All right. Thanks. It's really nice to be able to give this talk, and I apologize that I'm not there in person. It was a little bit of a short notice, and there are several other things going on. But I hope, nevertheless, to contribute something to this meeting. So this is a talk where I was asked to talk about dark matter, more or less at the level of a review. I've tried to keep it relatively, broad and not very technical, but I'm happy to answer questions if there are any. One more thing that I'll have to apologize for is that I don't have a lot of references or citations in these slides because I had to kind of slap them together on a relatively short notice. But again, if you need more references, please let me know, and I'll provide you all the references that you need. Okay. So just to start a little bit big, the main point is that there is a lot of evidence for dark matter, and this evidence comes from a variety of different probes. So here you can see in this cartoon, these probes are on the left, like cosmic microwave background, the structure of galaxies, lensing of light through astrophysical and cosmological objects, velocity dispersions in galaxies, rotation curves, and so on. And these observables at a variety of length scales in the universe. So it starts all the way, to the size of the observable universe, at the level of, clusters of galaxies, and then finally at the level of galaxies. At all these different, widely different length scales, there are a variety of these observables, which all have basically given us the same message, that there is more mass than can be observed using light alone. Okay, so now let me sort of build on that a little bit. So this mass, which we will now call dark matter, because it's not seen, but it's matter, so it's dark matter. One of the first lines of evidence for that was that galaxies, which, let's think of a spiral galaxy like the one that I'm showing here. There are stars, that are quite a bit far out to the edge of this spiral galaxy, and we can measure how these stars rotate around the center of this galaxy. And if you just apply, Newton's laws or Kepler's laws, so to say, you would predict that the speed of this star should fall off as 1 over square root of r, r being the distance from the center of the galaxy, as the star, as you pick stars that are further and further away from the center. And the reason is simply that as you go further away, you imagine that the mass contained in the galaxy is staying more or less constant, and then the distance is increasing, so the gravitational force is decreasing, and that's the reason that this velocity is supposed to decrease. But what was observed by Ken Ford, Vera Rubin, and others was that even when one goes pretty far from the edge of the observable galaxy, so in this picture you can see the galaxy roughly ends here, but then there are a few straggler stars a little bit further away, you can see that the rotation curve stays fairly flat. It is not decreasing as 1 over square root of r. Now, there are two ways this problem could be resolved. One is that, well, Newton's laws are wrong. Maybe something funny happens. And the other is that in this region where you're not seeing much of the galaxy, there's still a lot of mass. And we really have to then worry about why, is there all this mass here which doesn't form stars and we don't see it. So this was one of the first lines of evidence, the other being the very famous measurement of the velocity dispersion in the Coma cluster by Fritz Zwicky So, but these two early lines of evidence already told us that there was, the need for more mass, hidden matter in the universe. And over the years, over the decades, actually, this evidence has only strengthened. So this is one galaxy from M31. But then, here is a sort of collection of rotation curves. The radius from the center of the galaxy in kiloparsecs on your x-axis, and the rotation velocity on the y. And you can see that most of these rotation curves extend, to order tens of kiloparsecs and have no sign of slowing down. They're not, falling down. They're just basically flat. So then this isn't just one galaxy. This isn't just some outlier, but this seems to be happening everywhere. And the modern evidence for dark matter goes far beyond that. So while those two lines of evidence basically had to do with what's happening in individual astrophysical objects, we now have evidence on much larger scales, cosmological scales, that points to the same fact that the observed matter density and its fluctuations, that it tells us that there is some unseen non-relativistic matter, and I'll tell you why it's non-relativistic, that gravitates, that has mass and, behaves in a way that a normal mass would, but it doesn't interact much. And when I say it doesn't interact much, I mean that it does not, let's say, collide with protons and electrons, and it doesn't, let's say, shine light, by let's say getting excited and then emitting photons or any such thing. So all of these things that normal atomic matter does, the dark matter doesn't seem to be doing that. Maybe it does something like that, but at a strength that much more weak than we can measure currently. So that would be the second part of the talk, where I will come back to how we are trying to, find out more about dark matter. But at this point, it's fair to say that we have no evidence for any interactions of dark matter except through gravity. And the three main modern lines of evidence that we know of, one is through cosmic microwave background, one is through the structure of galaxies and how they're distributed over really large scales, and then the third being lensing of background light through matter in the midground. So to come back to this cosmic microwave background picture, what you see here on this plot is the inverse of the angular scale in the sky. And on the y-axis is the power spectrum, of temperature correlations. And it has this very typical wavy structure. And these oscillations carry a lot of information about the nature of the fluid that was undergoing acoustic oscillations at the time of recombination. And the heights and the positions of these peaks actually tell us about how much mass was there, how much pressure was there, and so on. And the fact that this third peak is almost the same height as this first peak and not lower, and also the fact that this tail is at this slope and not higher or lower, these facts then tell us how much matter there is which gravitates but does not interact with photons and therefore does not have radiative pressure. Okay, and from that we figure out that there is about 25% odd of the energy density of the universe that has to be in the form of matter that gravitates but does not interact with photons in a way that it would give radiation pressure. Similarly, one can look at the power spectrum of matter fluctuations, so we do that by basically counting how galaxies are placed on the sky. And that has this particular structure. And we just simply wouldn't have this if the universe just only had baryonic matter, which is to say that because they would be coupled to photons and then they would be kicked around in the early universe, and not allowed to form structures, until these photons had decoupled from the atoms. Whereas the structures that we have now are large enough and numerous enough that structures should have already started forming before baryons decoupled. And that's possible because dark matter decouples earlier from photons, and it starts clumping together, forming the potential wells. And then once the baryons decouple, they can fall into those potential wells, and then they form the galaxies and the galaxy clusters and so on. So this structure formation would simply not proceed, and would not have proceeded to the extent that it has if there were no dark matter. And then finally, there is this idea that if you have some distribution of matter in front of you, light can come from some background quasar or something, and you measure it, and sometimes you can see multiple images. And using this, you can build a map of the matter distribution in the lens. And this has been done for many, many lenses. And one finds that this matter distribution does not coincide with the light distribution. So again, there is evidence that there is more mass than is being seen. So these multiple lines of evidence tell us that there is mass. And the fact that this power spectrum actually stretches to scales of galaxies and somewhat, let's say, tenths of a galaxy, tells that whatever this matter was not moving very fast at the time that it decoupled from the rest of the universe. Because if it didn't, it would smear out structure on small scales. So this is free streaming. And the fact that this is not seen then tells us that dark matter must have been non-relativistic at the time it decoupled from the rest of the universe. So that's why this is called cold collisionless dark matter. Cold means that it does not move at high relativistic speeds. Collisionless means that it does not interact through the known particle physics interactions like strong interaction and electromagnetic interaction, and most likely the weak interaction as well. So at this point, we have to take a step back and we have to say that, okay, fine, there is evidence for some hidden matter that is only weakly interacting, and it's very non-relativistic. So what can it be? So we should first start asking, can it be just ordinary astrophysical objects like planets or old stars, or maybe black holes that we are just not seeing? And a simple way to say that that can't be all of dark matter is to say that all of these objects would have been part of like a primordial soup, and if they were made of just atoms, the same protons and neutrons and electrons that we have here on Earth, then they would have contributed to the radiation pressure, for example, in CMB, and that wouldn't work. So none of these ordinary stuff could be dark matter. So it has to be something else. Now, it could be that there is something fundamentally wrong with the equations, let's say Newton's laws or general relativity, that we use to infer these conclusions. But we won't go there today, and we would take the other option, which is that maybe that there is a hidden, yet undiscovered new particle in nature, or a set of such particles, which we will call dark matter, or nowadays often this is also called the dark sector, where you just expand the dark matter to include multiple particles and interactions. Now, that's what we know. And I kind of went fast over what we know because I assume that people have heard these talks several times, and I want to get to some of the newer stuff. And so it brings me to what we don't. So we don't know whether dark matter is a new particle or something else. We don't know if dark matter is, let's say, either a particle or let's say some clump of a certain kind, what is the typical mass of this particle or this clump or whatever? If it's a fundamental particle, what is its spin? Is it a boson? Is it a fermion? We don't know what this particle interacts with. Does it interact with electrons? Does it interact with protons? Because, for example, think of neutrinos. These are fundamental particles. Could they be dark matter? Because they only interact very weakly, mainly with electrons and other leptons. And could neutrinos be dark matter? Because they seem to fit the bill, because they have mass, they have no electric charge, they have at best very weak interactions. These weak interactions, the same ones that govern radioactivity, and so you wonder that maybe neutrinos are dark matter. But then they fail in one crucial way, which is that neutrinos, because they're so light, they would have been relativistic at the time of decoupling, and they would smear the galaxies to an extent that is inconsistent with current data. So therefore neutrinos can't be dark matter. So that's why a new particle. On the other hand, this lack of knowledge about what dark matter could be makes it incredibly challenging to then, work in this field and try to figure out what dark matter could be. The reason is simply that any search for properties of dark matter, beyond just its mass, the fact that it gravitates, has to depend on some property of dark matter. But we don't know what those properties are. So what's usually done is one makes an assumption, one makes a guess that, okay, maybe dark matter has the following properties. You just guess. I mean, there's no reason for that guess to be true. And then you go and test that guess. This strategy, which, is the best that we have currently, is extremely model dependent, basically by, its very nature, that you have to assume a model of dark matter in order to propose a search for dark matter. And then even after you do that, you're not guaranteed to succeed. And it's not because you can't build big detectors or you can't spend enough time or money or people to look for these dark matter particles, but just that suppose you made an assumption that dark matter is something that, let's say, interacts with electrons, and then I look for its interactions with electrons. I may never find it because maybe dark matter does not interact with electrons and it only interacts with, let's say, protons. And so you would need to build a proton experiment in that case. And then who knows how many such possibilities there are. So this is the real difficulty with the field of dark matter search, that we don't know of a model independent guaranteed way to look for it. This is very different from some of the other frontier problems in fundamental theoretical and experimental physics that we have solved in the last few decades. When it had to do with neutrinos, we knew that neutrinos had to interact with a certain strength. Although it was very low, we knew what strength it would have and we knew what it interacted with. Even for gravitational waves, because we had GR, we had a very precise prediction for what the strength of gravitational wave emission from, let's say, a merger of two black holes would be. But for dark matter, we have no such, theory prediction and therefore no such guidance to experiments. So we are left, in this mode of just trying to do every possible thing to look for dark matter. So the way it goes is theorists typically invent a number of dark matter candidates, models. These are classes of listed here. WIMPs, which basically was, it's like something like a proton without electromagnetic or strong interactions, and then it has a mass of, let's say, a few hundred GeV, like something like 100 times the mass of proton. And this is motivated by certain theoretical aspects of particle physics theories having to do with the scale at which electroweak symmetry breaks and the Planck scale. There are other candidates like asymmetric dark matter, where we assume that, well, it's precisely like the proton in the sense that there is a proton and then there's an antiproton, and then they can annihilate, and then whatever is left over, if there's, let's say, a little bit more protons than antiprotons, this leftover part behaves like dark matter. But of course, this is not a proton, but something completely new. But it has this particle-antiparticle-like feature, and we'll talk more about that. Then new particles called axions, a whole bunch of models. And then finally, maybe I will have some time to talk about primordial black holes. And each of these candidates is motivated by something or the other, usually some aspect of particle physics theory or just purely from aesthetic considerations. So let me discuss the first such idea. This is the classical candidate for dark matter, which is a WIMP. The idea is that there is a new particle, dark matter, called X, and it can annihilate. Two of these X particles can annihilate into two particles which are in the so-called standard model, the normal particles that we know of. And the opposite is also possible, that two of these standard model particles can also, combine to give you this dark matter particles, a pair of these dark matter particles. So when the universe is at a very high temperature, both of these reactions are going on, and X and SM, they are in equilibrium. As the temperature of the universe falls below the mass of the dark matter particle, this process of making dark matter stops, because you just don't have enough energy in the incoming collisions to make the X particles. But the annihilations continue, and the annihilations continue until the universe has become so dilute that these dark matter particles just don't find each other anymore. And then the number of these dark matter particles in any co-moving volume that gets frozen out. So this is called chemical freeze out of weakly interacting massive particle dark matter. So this naturally
Hi, Basudeb. Can you hear us?
Density, and then as a function of time on the x-axis, it first drops. Yes.
Sorry, we lost you for a bit. Just when you move to slide 9.
Slide 9.
The current slide, yeah. The WIMP miracle.
Yeah. So what I was saying was that in this WIMP-like models, dark matter forms out of a chemical freeze-out, which I explained in the previous slide. And here I'm just showing that pictorially, that at early times you have some density of dark matter given by its equilibrium density. And then as the universe expands, this density decreases exponentially, over many orders of magnitude, and then freezes out to some co-moving density, which is then observed. Turns out that if you choose the mass of these dark matter particles at roughly this 100 GeV scale, and the interactions at the same scale as would be given by usual weak interactions, you get the correct observed abundance. This is called the WIMP miracle. Of course, you can adjust the mass and the interaction strength to achieve this number, but even when the mass is not 100 times the mass of the proton and the interaction is not exactly the weak interaction strength. But the beautiful part is that for weak interactions, which is being shown in this red line, you actually have a very large range of masses of the dark matter, where you end up getting this same observed density, almost the same observed density. There is only a very weak sensitivity to the dark matter mass. And that's precisely what's shown by these dashed red lines. So you go from 1 GeV to 1000 GeV, and you can see that these curves more or less converge to the same place. Okay, so this is the WIMP miracle. Now, this was one of the guiding, ideas of this field, and in the 70s, this was calculated, and about 10 years ago, when experiments started probing the rate at which these dark matter particles could annihilate, it became very important to make a more precise calculation of this process. And now we can compute the cross section that you need as a function of dark matter mass to about 4%. And that's shown here. Okay, so now this is the idea. You can look for its annihilation, happening in astrophysical objects, and this gives rise to a very large variety of experiments. So the scattering in your lab, of a dark matter particle coming from space, this is called direct detection. We haven't seen anything yet, but we have improved the exclusion on, let's say, the cross section by 10 orders of magnitude or so over the last decade and a half or something. Colliders have also failed to see any sign of such WIMP-like dark matter, and so have indirect detection. So, we imagine that dark matter annihilates in some nearby galaxy, or let's say the center of our own galaxy, and then we are looking at the products of such annihilation, and we haven't found any excesses. This is not for the want of trying, because there are a variety of experiments looking at different channels, different messengers, if you will, different set of astrophysical objects where dark matter could reside, and yet there are no compelling, let's say, signals. The strategy here has been always to look for places where there's a high signal to background ratio. You look for some morphological signature or a spectral feature, and you try to look at the same object in two different messengers, or in the same messenger in two different sources, to make sure that you're not being fooled by some kind of background, some astrophysical source of the same signal. Okay. So one of the cleanest sources have been dwarf galaxies, where you look for annihilation of dark matter inside small dwarf galaxies, and they give some of the strongest limits on dark matter annihilation, which actually now go fairly below this benchmark cross-section that one needs at these masses to produce the amount of dark matter that we see. So, this is a field that there has been tremendous amount of success, but not the real success of discovering dark matter. So let me skip this. I think I'm doing really badly with time. Is it, Prayush? How much time do I have?
You can take, I think, around 5 to 10 minutes more. We have.
Okay, so let me try to take somewhere around 5 to 7 minutes, maybe max 10. So, okay, so this was the first idea, WIMPs. And then there are small deformations of these ideas, that WIMPs are thought to interact very weakly with standard model particles and also with themselves. But if you allow these WIMP particles to have stronger interactions with each other, which is not ruled out by data, then you get something else and you can look for it. And the thing that you get is that it changes the structure, the density profiles of dark matter halos in small objects like galaxies and the centers of these galaxies. So if you have WIMPs, you get very sharp, 1 over R like densities. Of course, they can be corrected somewhat by the effect of stars and supernovae and so on. But dark matter predicts this 1 over R kind of density, which is called a cusp. And if you have the self-interaction, then it becomes more like a core. And you can then go and look for rotation curves and try to figure out whether it's a cusp or a core and so on. And there's a lot of work here, which for the want of time, I will skip. The other idea, which is kind of different from WIMPs, where you will say that, well, now dark matter cannot annihilate with itself, but there is a dark matter and there's an anti-dark matter, and they annihilate, and what you're left with is just the excess dark matter. Okay? And this excess dark matter, this is what you're left with. This is what we call dark matter now. This can't annihilate anymore. So it can just keep accumulating somewhere, and you go and try to look for it. one of the motivations for these kind of models was to predict why the observed abundance of dark matter, which is about 25%, is, let's say, within a factor of 5 of the observed abundance of ordinary matter, so protons and neutrons and so on. So there are a lot of papers here, and again, it's not worth going into all of them. But the idea is that this kind of dark matter has a very distinctive signature. Because it cannot annihilate, it can accumulate without end in big astrophysical objects like stars, let's say neutron stars. And because they can accumulate under certain conditions, in particular for heavy dark matter, this accumulated dark matter can collapse, under its own gravity, and that can give interesting effects on its host star. And this can be used to set constraints on such dark matter, and this was done somewhat recently. So there are other tests of asymmetric dark matter, but this is something that we did, and I wanted to mention it. A very popular idea these days is axion dark matter. This is a completely different beast. The idea is that in the theory of quantum chromodynamics, which is what explains the dynamics of quarks and gluons, the stuff inside nuclei, we need to explain why the electric dipole moment of the neutron is so small. And one of the ways to do it is to postulate a new particle called the axion, which dynamically basically turns the electric dipole moment of the neutron off. And the price of introducing this Pechoquin field is that then you predict a new particle which is very light, and it's a boson, it's a pseudoscalar, and it has an interaction with E dot B. So the interaction goes as axion interacts with the product of electric and magnetic fields. And so this is a particle that then you can look for using, let's say, a cavity where you have a magnetic field. And then if an axion comes into your cavity, that axion can convert into an electric field in the cavity magnetic field. And so this is like a radio that's looking for axions. So this has become an incredibly active field over the last decade. And this is one of the sort of bird's eye view plots that shows the kind of thing that's going on. On the x-axis is mass of this axion particle. You can see the 19 orders of magnitude that it spans. On the y-axis is the strength of this axion interaction to E dot B, or like 2 photons, if you will. This yellow line is what is predicted as a solution to this strong CP problem, or this neutron electron dipole moment problem in QCD. And all these other colored shaded regions are exclusion contours from a variety of experiments. So this is, of course, very complicated looking. So here is a simplified, ultra simplified version. But basically, you find that laboratory searches for these axions, where axion converts, so where a photon can convert to an axion, that rules out large couplings. Otherwise, some photons would get lost to axions in the lab. Similarly, the fact that light from stars isn't, dimming in some unexplained way gives you these green bounds from astrophysics. This gray shaded region are other bounds on axions in the form of dark matter from astrophysics, for example, from its free streaming length. And then this bound, which is at very small masses, basically says that if this dark matter, which is forming of axions, would be so light, it would have a very large de Broglie wavelength, and galaxies would get smeared. So again, that's not allowed. So you can see that we basically ruled out a lot of parameter space, but then you can also see that there's a lot of parameter space that's still left to be covered. So this is a very exciting field with a new idea coming up every week or so. Then finally, here is another idea for what dark matter could be, and I stole this slide from Ranjan Laha, who was scheduled to give this talk. So the idea is so far I've been talking about some new fundamental particle that makes up dark matter. And I told you that ordinary matter could not be dark matter because all ordinary matter early enough in the universe was part of this primordial soup, and therefore it would have contributed to radiation pressure in the CMB, and that just doesn't work. But there is one exception, which is that even before decoupling, even before recombination where CMB was forming, much earlier than that, this primordial soup, whatever it was, it had density fluctuations. And some of these density fluctuations, if they were too large, they could collapse and form black holes even before anything else happened. These black holes, which are called primordial black holes, they are still allowed as a dark matter candidate. In a sense, this is extremely minimal because you don't have to invent anything new. You don't have to postulate a new particle. This is an extremely minimal idea. The difficulty with this is that you do not easily produce these large density fluctuations early in the universe in sufficient, frequency over the whole universe to give the observed amount of dark matter. Basically, the reason is that the typical fluctuation that we see in CMB is of the order of 10 power minus 5. And if you take that to be the variance of, the density field, you predict to get an order 1 density fluctuation, you have a very, very low probability. But this extrapolates the Gaussian density fluctuation probability distribution to the very tails, which of course isn't right. So that's where we stand. So it isn't clear that we can make primordial black holes very easily, but we can't rule out that we can't make these primordial black holes. Now, depending on when these black holes form, these primordial black holes, they have a different mass. It's given by how much mass is contained in the horizon at the time of their formation. And that's this mpb, just 10 to the 15 grams for formation time divided by 10 power minus 23 seconds. And so they can have any mass you like, depending on when they form. And they typically have, they're believed to have a log normal mass distribution or a power law type mass function, and they can have a wide range of spins. This black holes can also spin. Now, people have looked for these primordial black holes, and what you have here on the y-axis is the fraction of dark matter in the form of these primordial black holes. This is 1, and this is 1 part in 10 to the 4. And on the x-axis is the mass of this primordial black hole, above in solar mass and below in grams. And these shaded regions are constraints from a variety of things. So these colored constraints are from the fact that these very small, tiny primordial black holes, they have a high temperature, and therefore they Hawking radiate very efficiently. The fact that we don't see unexplained radiation, from these Hawking radiation of primordial black holes rules this out. And these other shaded regions come from things like non-observation of lensing from these primordial black holes or from their impact on the CMB, for example. So there are a variety of bounds, but there is this gap, roughly what is called the asteroid mass range, where primordial black holes can form all of dark matter. So this is very exciting, and one should look for ways to search for primordial black holes in this mass range. And there are interesting ideas. So this is my last slide before we end. And so although this is not part of the main theme of where I was going, of late there's also a good bit of work that tries to use gravitational waves as a way to look for dark matter or some properties of dark matter. And I've listed a few here, and I'm leaving this for maybe the discussion session where we can maybe discuss this more. But without taking further time, let me just get to my summary. So the evidence for dark matter is overwhelming, but its identity is a mystery. So what we know is that dark matter exists, and what we don't know is that what it is. There are a number of ideas, new and old, and I've listed some of them here. And the way we are proceeding is we are trying to test each of these ideas to the best of our technological abilities. And some of the most recent excitement in these areas has been in the field of axions, primordial black holes, and the use of gravitational wave techniques to look for certain features of dark matter. So, with that, I'll stop and I'll take any questions if there's time.
So we have time for maybe a couple of quick questions before we move on.
Thank you for the great talk. I had a very quick question about one plot where you showed constraints from the Lug Zeppelin experiment. And the current constraints seem to be getting uncomfortably close to the neutrino fog. I wanted to know your thoughts on what's the way forward if you touch it.
Yeah. So, okay. So, thanks for that great question. Gives me an opportunity to talk about the neutrino fog. So, as I told you, the colored regions above are basically ruling out interaction strengths at given masses. And this blue shaded region or the gray shaded region down basically tells you a region where the interactions typically with solar neutrinos in your detector give you a signal that's larger than the expected signal from dark matter. So once you have ruled out all the white region above this gray region, what can you do? Because you will always have this noise in your detector coming from neutrinos, and then can you still say something about dark matter? So this is, of course, a very difficult question, and I'm not aware of good answers. People have looked at directional detection, but this is very hard. So if you can somehow build a detector where you know which direction the dark matter is coming from, then much of this blue background in the neutrino fog can be cut down, but it's incredibly difficult to scale to large experiments which are directionally sensitive. Other than that, you can maybe use things like day-night or let's say annual modulation of the dark matter signal, but I'm not aware of great ideas. Yeah.
So, hi Basu, you
Going to be
mentioned.
difficult.
Okay. So, hi Basu, you mentioned that the particular this self-interacting dark matter will show up in the galaxy rotation curve, and there is also another variety of dark matter like which can accumulate in the inside of the neutron star.
Yeah.
So, this too, we have a lot of galaxy curves already. We have observed rotation curves, and we have a couple of good idea about the neutron stars also. So, what do you think the current constraints are, and whether how far we are from ruling out at least this two variety of dark matter?
Yeah. So again, I apologize. I probably went too fast over this. So some of these are showing you constraints on models of self-interacting dark matter, from the fact that they should not change the CMB, or the fact that they should not change the rotation curves beyond some point, or they should not change some combination of the matter spectrum and CMB and so on. So there are constraints. By and large, the constraints are in the range that the interaction strength is 1 centimeter square when the mass of the particle is 1 GeV, I think. Is it? I am not sure if I'm getting that right. Anyways, I don't remember the precise number. 1 centimeter square per gram, or maybe someone who's an expert should remind me the number. But there are constraints. These are roughly at the same level as 1 centimeter square per GeV. That's correct. The cross section at which neutrons would interact. That's roughly where the current constraints stand. Maybe a factor of 10 stronger. Can we do better? Yes, there's a lot of work going on, and I'm not sure if Sushmita is in the audience or she's online, but Sushmita Adhikari and several others, they're working on these kind of things, and they can tell you a lot more. Maybe we will have a time to discuss more of this in the discussion. But yes, there's a lot of work going on here.
Okay, thank you. So in the interest of time, let's push further questions to the panel discussion later. And let's thank Basu again for the very nice overview.